a potential due to a charged particle. So we had to find an expression for electric potential V in a point located in a space around a charged particle. Let's say there is a charge Q here. So it will have an electric field and a radial directions. So we had to find electric potential at point P at a distance r from the charge plus Q here. So here let's discuss that. Actually, I am bringing a charge from infinity to that point. So we can define electric potential at that point R will be equal to minus of integral infinity to R e dr. So we know potential electric field due to a charged particle at point P at a distance r from the charge will be equal to we know that is equal to, so E will be at that point will be equal to K Q by R square, or K is 1 by 4 pi epsilon 0 Q by R square. So that means I can take Q by 4 pi epsilon 0 outside, then I integrate from R to infinity to R 1 by R square. So if I integrate 1 by R square dr, I will get this as r raised to minus 2 plus 1 divided by minus 2 plus 1 from the limit is infinity to r. So infinity to r, that will give me r raised to minus 1 over minus 1 from the limit infinity to r. So that will be this is, I can just say that this is r raised to minus 1 by minus 1 because minus 1 by r. Let's say infinity to r. So you can see 1 by this will, if I give the first limit, that would be minus 1 by r minus 1 by infinity. 1 by infinity we define as 0. So the integral of integral infinity to r 1 by r square dr, we get it as minus 1 by r. So it all become minus 1 by r, this integral. So there is minus sign, that become plus. So potential at a point P from a charge Q is defined as V of r is 1 by 4 pi epsilon 0 Q by r. That is if you change r instead of r, radial distance r from a point charge, we can say potential is equal to 1 by 4 pi epsilon 0 Q by r. Or if you replace 1 by 4 pi epsilon 0 by K, we can write the potential at a distance r from a charge Q is equal to KQ by r. So electric potential due to a charge Q is at a radial distance r from the particle is given. So a potential may be positive if Q is positive, potential may be negative if Q is negative. Let's discuss a question here. Here is a question. The two charges minus Q and Q are placed at a distance minus Q is at a L distance from the origin. Let's say this is origin. Let's say this is origin. So from the origin, this is L. Other charge is at a distance 2L from the origin, and this point P is at a distance 3L from the origin. So what they say is basically they say that at point P electric potential is 0. So point P at a distance is one of the 2 points on the x-axis at which electric potential is 0. This is they are saying that there are 2 points along x-axis where potential is 0. P is the one of that point. So question is, how far from the origin is the other point? What is the other point? So before doing that, let's verify that potential here is 0 itself, right? Remember, potential is V is a scalar, so you don't have to consider the vector sign in doing these calculations. So here let's see it is minus q. So here, right, what is the distance between minus q and p? This distance from here to here is L plus L, that is 2L, right? So what is the distance between q and p here? This is L. So potential, let me call this as q1, let me call this as q2, right? So potential at point P will be equal to potential due to q1 plus potential due to q2. You are just adding that, actually these are scalars. So potential due to q1 will be minus, because it's minus, it's 2q, so we can say that k2q divided by r from here to here is 2l, let's say that is 2l, plus another one is k q by r. Here k is, so k into q here is plus q, r is from here to here, that is the distance is L here. So you can see that actually. So here 2 cancels, so it is minus kq by L plus kq by L, that gives you 0. So it's confirmed that at point P electric potential is 0. Now the question is, there could be another point where electric potential is 0 in between them. Let's think that electric potential is 0 somewhere here, right? Let's say electric potential is here at a distance from here to here, let's say it's x. At point x electric potential is 0, right? Then if you think that what is the distance from here to here, the distance here total here is x, so you need only the distance from here to here, so this distance will be L minus, sorry, that is from here to is x, so it will be x minus L. What is the distance plus q will be from here to here? That also will be from here to here, it is 2l minus x. So from the distance from here to here will be, total distance from here to here is 2l. If you subtract of x, you get the distance here. That means here is 2l minus x. So let's find the potential at a point here, that is x distance from the origin. So let's find what is x, right? So how to find it? Let's say we say that it is potential is 0, so then that is equal to 0. Then it will be k into minus 2q divided by the distance from here to here, that is x minus L, plus k q by distance from here to here is 2l minus x, that is 2l minus x. So we can say that their potential is 0, then we can say that minus 2q minus 2q into k 2q by x minus L, minus this goes, actually I take them this one side, so that will be equal to kq by 2l minus x. What I did actually is 0, I take this other side of the 0, that is become positive. So here kq and kq cancels, and what we are left with is 2 by x minus L is equal to 1 by 2l minus x. So we need to find x, so let's cross multiply this. This goes here, this goes here, so that gives me 2 into 2l minus x is equal to x minus L. So let me open this bracket, so 2 into 2 will be 4l minus 2 into x means 2x equal to x minus L. So let me bring x into one side and L into other side. So the minus L comes here, this will become plus L, that will be 5L here. So minus 2x goes other side, that become plus 2x here, that will become 3x here. So we know 5L is equal to 3x. This gives me x equal to 5 by 3L. 5 by 3L means it will be around 1.6L. So somewhere here, right? So that is a point. Another point from the origin where potential will be 0 will be x equal to 5 by 3L. You can cross multiply, you can check that potential here is 0 again. Do potential the same thing and check whether potential here is 0 when x equal to 5 by 3L. So potential due to a group of charges. Let's say there are many charges here. So we know potential due to a charge will be kq by distance from here to here, right? So there are many charges. So what is the total potential at the point P? So that will be equal to the potential, because potential is a scalar. So potential due to this plus potential due to this plus potential due to this. That is, potential here will be total potential I equal to 1 to n. That means potential of this V1 plus V2 plus V3 plus V4. That what we write here, it is here you can say what is the summation here. That means V1 plus V2 plus V3. That is by summation what we mean here. So you can also say that this is equal to 1 is 1 by 4 pi epsilon 0 q1 by r1 plus 1 by 4 pi epsilon 0 q2 by r2 plus 1 by 4 pi epsilon 0 q3 by r3. I here means just is running from 1 to n. When I equal to 1, this become q1, this become r1. So r1 is a distance from q1 to p, r2 is a distance from q2 to p, r3 is a distance from q3 to p. So here this is algebraic sum, means if this is positive, here it will be positive. If this is negative, this will be negative. Here this is negative, this also will be potentially will be negative for that. So let's do a question then. Here we have 4 charges at 4 corners of a square. I need to find the potential at P at the center of the square. So here distance between the charges is d is 1.3. So here charges for the each so q1 is 12 nanocoulomb, q2 is minus 24 nanocoulomb, and q3 is 31 nanocoulombs, and q4 is 17 nanocoulombs. So how we find it? So we can say that electric potential is R is same here from here to, because if it is a square, this R, this R, this R, and this R will be same. So what will be the potential here? This will be, if you say that actually V1 will be equal to KQ1 by R. What will be V2 will be equal to again KQ2 divided by R, because R is same here, right? And similarly V3 will be equal to KQ4 divided by R. This is KQ3 divided by R. So first we find the R, because this is, because if you think about it, this is using Pythagoras theorem. This will be d by 2, then this also will be d by 2, so at the center. So you can say that R will be equal to square root of d by 2 square plus d by 2 square. Then you can, if you do that, it will be 2d square by 4. That gives you d by root 2. So d is 1.3, so 1.3 over root 2, you get 0.919. So we got R now. So let's find the total potential at P. So how we do that? We know potential at a point will be potential due to V1 plus potential due to V2 plus potential due to V3 plus the Q3 is potential due to Q4. So that is v1, v2 and v3. So if you do that, that will be k into q1 by r plus k2 in q2 by r. Because k I take common means k is, I can take k common, so it's q1 by r plus q2 by r plus this is um, q3 by r plus q4 by r. So let's put the values. So r is also common, I take r also outside, so q1 plus q2 plus q3 into q4. So here put the here q1 is given 12 nanocoulomb, q4 is, because nanocoulomb I can multiply each by 10 power minus 9, so I can multiply that outside 10 power minus 9, because every number here is multiplied by 10 power minus 9. So 12 into 10 power minus 9 minus 24 into 12 power minus 9 plus 31 into 10 power minus 9 plus 70, because the signs are depending upon the signs of the charges here, right? So if you do that, I get actually total potential at P due to all this charge configuration is 353 volt. So here is a question. What the question says, there are 4 charges as shown in the figure. You need to find what is the net potential at the center of the square. So again the same thing here. Let's say this is q1, this is q2, let's say this is q3, and this is q4. So there will be distance from the charges, at least r, and this is same for here and here and here and here, because this is a square, so all distance from the charge from here to here will be same. So what is that actually? Here we know that V at P will be equal to potential due to V1 plus potential due to V2 plus potential due to V3 plus potential due to V4. So that will be here because KQ by R, K Q1 by R is same, plus K Q2 by R plus K Q3 by R plus K Q4 by R. So Q1 is plus Q. I can take K by R outside, K by R into Q1 is plus Q, Q2 is also plus Q, plus Q3 is minus Q, plus again this is plus Q. So here it will be, you can see minus Q plus Q cancels. We have actually here K by R 2Q. So potential at P will be equal to 2K into Q divided by R. So if you know the distance x is given, if you know the x, you can find, you can say that what is the x. Remember, this will be x by 2. This also will be this also here, this will be x by 2 from here, so this also will be x by 2. So R will be equal to square root of x by 2 whole square plus x by 2 whole square. That will be x square by 4 plus x square by 4. That becomes 2 times x square by 4. So that you can say that x square by 2. So square root of x square is x, square root of 2 is root 2. So x by root 2 you can get. If you know the charge of Q, you can put that K is 9 into 10 power 9, and you can find the actual values if I give you the actual values of Q and X. So here's another question. Here actually what the thing is, there is plus Q, minus Q, plus Q and minus Q. So there are actually equal number of positive and negative charge in R. It will be, you can say that potential will be 0 here. So here how it is, again potential will become, let's say this is Q1, it's Q2 and Q3 and Q4. So V at P will be equal to V1 plus V2 plus V3 plus V4. So that will be equal to here, let's say this is from here is R, n is a square, all distance from here and here and here will be r. So we can say that that is k q1 by r plus k q2 by r plus k q3 by r plus k q4 by r. So that will be equal to k by r. I can take outside k by r into q1 plus q2 plus q3 plus q4. So that will be equal to so k by r, and q1 is here plus q, q2 is minus q, plus q3 is plus q, q4 is minus q. So you can say plus minus q cancel, plus minus q cancel, that is then all cancel. So this gives you 0, k by r into 0, that is equal to 0. That means potential at P will be 0 in this case. So here V at P is equal to 0. So here is a question, that is there are 12 electrons. That means just like a clock, each are placed at equal distance from the circle. 12 charges placed, they are same charges, is minus charges my electrons, so they are minus E. So what is the question? So we always say that V at infinity is 0, that's why we define electric potential. So what are the electric potential and electric field at center C? So what will be the here, because the distance from here to, let's say this is q1, q2, etc. So it will be q3, q4, q5, q6, q7, q8, q9, q10, q11. This will be q12, like that. So distance from here is for all will be r, right? Everyone have around the circle, so r. This then potential at C will be equal to k q1 by r plus etc., like that, right? So you can say that it is q2 by r plus q3 by r, like that. So you can say k by r into q1 plus q2 plus etc. plus up to q12. So here charge is minus E, everyone will be minus E, minus E, minus E. That is actually you have k by r into minus 12E, right? So here electric potential at center will be minus 12, minus k 12E by r, or you can say 12 ke over r, or minus. This will be the potential at that point. So now what is the other question? Next other question is, what is the electric field here? So you can see electric field due to this charge will be towards this, right? So this will be the direction of electric field here. So R is same. So electric due to a point charge Q is electric field due to a point charge, right? At a distance r from the charge will be kq by r square, and this is a vector along the, if for electric field is towards the negative charge and away from the negative charge. So this is radially outward, so it is towards it. So you can say radially outward. So kq by r here. So here you can say if you take this positive, this direction should be negative, right? So here electric field is same kq by r but in opposite direction, right? So minus of r. So same actually, so this electric potential, so electric field cancel with this, so this cancel with this, and this cancel with the other one. So total electric field here will be equal to 0. You can also say that according to Gauss theorem, electric potential at C will be 0 if you consider any point here. So you can say that E dot dA is equal to Q enclosed by epsilon 0. Q enclosed is 0, so potential at this point C will be 0. So that's all, boys, for this section, and we will continue with next video. I will talk about the continuous charge distribution, how the electric potential, how can we calculate the electric potential when there is continuous charge distribution.